Hey there, and welcome to this explainer. Go ahead and get comfortable, because today we are taking a highly visual, conceptual journey straight into the strange, honestly mind-bending world of quantum mechanics. We're going to completely set aside the heavy math equations, and instead, we're going to build a brand new mental model of how computation actually works.
Okay, let's just jump right in and play Mythbusters for a second. Is a quantum computer just a super fast classical computer? Well, the answer is a massive, resounding no. People naturally assume that because it has the word computer in the name, it just does exactly what your laptop does, but maybe millions of times faster. Actually, that couldn't be further from the truth.
Think of it like this. A classical computer is like a bicycle, and a quantum computer is like an airplane. Sure, both of them provide transportation, just like both computers process information, but they operate on entirely different physical principles. I mean, an airplane isn't just a bicycle with really, really fast pedals, right? It literally uses aerodynamics to leave the ground entirely. Quantum computers are doing the exact same thing, but with information.
Section 1. Not just a faster computer, bits versus qubits.
So every single device you own right now, your phone, your laptop, even the massive servers running the internet, they all use classical bits. Try to imagine a classical bit as a very rigid light switch. It's strictly on or off, a 1 or a 0. Every photo, video, and AI model eventually just breaks down into billions of these rigid little switches. But quantum computers, they use qubits. And instead of a switch, think of a qubit as a spinning coin. While that coin is spinning in the air, it isn't purely heads or tails. It exists in this dynamic blur of both, simultaneously.
Let's actually look at the math of that spinning coin in action, because what's really wild here is how quantum information spaces grow exponentially. With 3 classical bits, you can only store one single combination of 1s and 0s at a time. But 3 qubits? They can represent all 8 possible combinations at once. By the time you scale up to just 50 qubits, you are representing 1.1 quadrillion states simultaneously. It grows so fast, it leaves classical memory completely in the dust.
All right, Section 2. The 3 core quantum principles. That brings us to the first quantum superpower, which is superposition. We just touched on this with our spinning coin analogy, right? It's the ability to exist in a combination of multiple states at the exact same time. This is what lets a quantum processor manipulate massive numbers of possibilities at once. But, and this is a really important caveat, this does not mean the computer just magically tests every single answer at once and instantly spits out the correct one. If it worked like that, literally every problem in the universe would be easy.
The real magic, the thing that actually finds the answer, is the second superpower, interference. Think of quantum waves exactly like ripples in a pond. When you toss 2 stones into a pond, those ripples interact. Sometimes the peaks of the waves add together to make an even bigger wave. That's constructive interference. But sometimes a peak meets a trough, and they just flatten each other out completely. That's destructive interference. Quantum algorithms are carefully, brilliantly designed so that the paths leading to the wrong answers cancel each other out, while the paths to the right answers reinforce each other, building up like a giant wave.
And then we have the third superpower, entanglement. Think of this one as 2 perfectly linked magic coins. When qubits become entangled, their states are permanently tied together. If you measure one, you instantly, and I mean instantly, know the state of the other one even if they are separated by huge distances. Einstein actually famously called this spooky action at a distance. This wild property creates correlations that are just completely impossible in classical physics, and it powers essential logic gates like the C0 gate.
Moving on to Section 3. The catch: extreme cold and fragile qubits.
Okay, so with all these superpowers, why isn't your next smartphone going to be a quantum one? Well, it comes down to some really massive physical hurdles. The leading superconducting circuits built by companies like IBM and Google have to be kept unbelievably cold to work. We are talking about operating around minus 273.15 degrees Celsius. That is hovering right above absolute zero, which makes the inside of a quantum computer literally colder than the vacuum of deep outer space.
So why exactly do they need to be that cold? The answer is decoherence. You see, qubits are almost unbelievably fragile. The absolute slightest bit of heat, a tiny microscopic vibration, or even just a stray electromagnetic wave can cause decoherence. That environmental noise literally destroys the delicate quantum state. Basically, it knocks our spinning coin out of the air before it even has a chance to finish calculating. Overcoming decoherence is without a doubt the single biggest engineering challenge in the field today.
Because of this extreme fragility, scientists say we're currently in what's called the NISQ era.
That stands for noisy intermediate scale quantum. Basically, it means our current hardware does have hundreds, maybe even thousands of qubits, but they are highly imperfect and very noisy. In fact, we actually have to group a whole bunch of these error-prone physical qubits together just to create one single, reliable, error-corrected logical qubit that we can actually trust.
So it might feel a little jarring to compare, say, an Apple M3 Max processor with its 92 billion transistors against an IBM Condor quantum processor that only has 1,121 qubits. But remember, this is not an apples-to-apples comparison at all. Transistor power grows linearly, but qubit power grows exponentially. Those 1,121 qubits represent an impossibly massive computing space, even with all the noise we just talked about.
Section 4. The timeline of progress. Let's trace this journey really quickly. Back in 1981, the legendary physicist Richard Feynman first proposes the idea of quantum simulation. Then, by 1994, Peter Shor develops an algorithm proving that quantum computers could, in theory, one day break modern cryptography. Fast forward to 2011, we get the first commercial systems from D-Wave. Then we hit a massive headline-grabbing milestone with Google's Sycamore in 2019 and march steadily into 2023 with IBM's Condor reaching over 1,000 qubits. It's moving incredibly fast.
Now, you might have noticed that Google's 2019 milestone mentioned the word supremacy. Let's define what that actually means. Quantum supremacy happens when a quantum computer performs a specific, highly specialized task that would be totally impractical for a classical computer. Now, let me be super clear here. This didn't mean your everyday laptop suddenly became useless for web browsing or sending emails. It simply proved that for incredibly specific, complex math problems, quantum logic could solve in minutes what might take classical systems thousands of years. And finally, Section 5. Why quantum computing matters. Let's connect those spinning coins back to some massive, real-world breakthroughs. Because quantum computers can simulate nature at a molecular level, which is something classical computers fail at pretty miserably, they are poised to completely revolutionize drug discovery and material science. They can also tackle incredibly complex optimization problems for global logistics. They could supercharge machine learning and AI well beyond our current physical limits, and, yes, thanks to Shor's algorithm, they are absolutely going to force us to reinvent global cryptography from the ground up. Ultimately, we aren't just building a faster bicycle here, we're quite literally learning how to fly. So I want to leave you with this to ponder. When we finally tame the noise and we perfectly stabilize those spinning coins, how will fundamentally rewriting the rules of computation change our future? The quantum frontier is completely uncharted, and it's going to be a thrilling ride. Thanks so much for joining me for this explainer, and keep that curiosity alive.